Gambling, winning and losing streaks, and the standard deviation. Part 2, unfair games. In part 1, we saw how the deviation in the expected return changes with the length of play. This concept becomes important when we move from a fair coin flip game to an unfair casino game. Here I've set up another simulation with two gambling games plotted on the same graph. The black line shows the change in bankroll for a fair coin flip game, while this red line shows the same thing for an unfair game, betting on red at roulette. For a standard American 2-0 wheel, the chance of winning is 18/38 and the house edge is 5.3%. I triggered the win-loss decisions on the same sequence of random numbers. So the fair and unfair game results are correlated. The win-loss decision for the two games is usually the same, but randomly, about 1/38 of the time, the roulette bet loses when the coin flip bet wins. So after 400 bets, the roulette game is behind the fair game by about 21 bets. These horizontal lines are spaced at 20 bets, which is the standard deviation of the win or loss for a session of 400 bets. I'll press the key several times to generate a new sequence of 400 bets. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You can see that the roulette results fall behind the fair game by about 21 bets in each session. So you need about one standard deviation of positive good luck just to overcome the house edge and break even. What about sessions longer or shorter than 400 bets? Let's take another look at the summary table for the fair coin flip bet first. The chance of a positive final result is 50%, no matter how long you play. The unlucky and lucky session results are centered on the average final return, 0. Here's the table for the roulette even money bet. The number of plays in this column represent one single spin and roughly 1 hour, 1 day, and 1 week of playing roulette, 1 bet per spin. The standard deviations are the same as before. For a single spin, the chance of a positive result is 47%, a nearly even game. For a 1-hour session, the average loss is 3 bets. An unlucky session, 1 standard deviation down, is a loss of 10, and a lucky session, 1 standard deviation up, is a win of 4. The chance of a positive end result is still decent, 35%. For a 1-day session, the average loss is 21 bets, and even at plus 1 standard deviation, you're barely breaking even. This is what you saw in the simulation. The chance of a positive result is 15%. For a 1-week session, you can expect to lose 130 bets on average, and you can expect to win 47% of the bets you make, plus or minus 1%. To come out ahead at the end of the week, you need good luck at the plus 2.6 standard deviation level, which will happen a little less than 0.5% of the 1-week sessions that you play. Now let's take a look at a better bet, the pass bet in craps. The chance of winning a single bet is 49%, which is close to an even game. For a 1-hour session, the average loss is 1 bet, and the unlucky and lucky end results are almost equal. Your chance of coming out ahead is quite good, 46%. For a 1-day session, the average loss is 6 bets, and the chance of winning is still a decent 39%. For a 1 week session, you can expect to lose 35 bets on average, and your chance of ending up ahead is 24%. Not great, but certainly better than roulette. These good results apply only to the pass and don't pass even money bets. Many craps bets have a house edge as bad as roulette, or even worse. However, there are some craps bets with a house edge of exactly 0, which is the subject of another video. In summary, the shorter you play, the better your chance of winning, and conversely, the longer you play, the more certain it is that you will lose. Playing a game with a smaller house edge helps tremendously, especially if you play a long time. So far, we've looked only at even payoff games. What about an uneven payoff game like betting on a lucky number at roulette, which pays 35 to 1? That's the subject of part 3.